Good morning. This is your Stat Sensei, and welcome back. I'm glad you came back. So for a given, and we're talking about sample size. I'm sorry, we're talking about sample size, and we're going to work through a bunch of multiple choice questions on this. For a given large sample size, which of the following gives the smallest margin of error in calculating a confidence interval for a population proportion? So we're working with this formula: p hat plus or minus z star p hat q hat over n. And please remember, this is my margin of error. Now, one thing you have to keep in mind, as we increase our confidence level, z gets bigger. Well, z gets bigger, we're multiplying. So the larger the confidence level, the wider the width. So as our confidence level goes up, the width also goes up. So we need to find the answer with the largest confidence level. Well, this one has the largest confidence level, okay? And the next thing is, and this is a kind of bit odd, and by the way, this problem is going to be an issue for us. The smallest, they want to give the smallest margin of error. I'm sorry. So we're looking for the smallest margin of error. So as the confidence level goes up, the width goes up. So we're going to want to have the smallest confidence level. Well, 99 is our largest. 95 is our next largest. So we're going to be looking at one of the 90s as having the smallest confidence level. Well, the next thing we need to look at is p hat. Okay. Well, the smallest confidence level is going to be the farthest away from 0.5. And here's what happens. P hat, this would be 0.15, and Q hat would be 0.85. And when I multiply them, 0.15 times 0.85 is 0.1275. So that's 0.1275 versus the other one, which is 0.23 times 0.77 equals 0.1771. And I'm going to be looking for the one that's the smallest. Well, this gives me the smaller value, so this will have the smallest width. All right, because we want the numerator to be as small as possible. So smallest numerator, smallest width. So the 90% with the smallest width, which is the 0.15. And what I was getting at is there's kind of a rule of thumb. Well, it's not a rule of thumb, it's a fact. The farther your p hat is from 0.5, the farther it is from 0.5, the smaller the interval. All right, so if this had been 0.01, it would have been even a smaller interval. All right, so the next one. 295% confidence interval estimates are obtained. This one has a width of 6. This one has a width of 7.9. If the sample sizes are the same, in other words, given the same, what has a larger standard deviation? Well, the larger the standard deviation, the larger the width. So once again, as this goes up, width goes up. So in this case, we go, oh, the second one would have the largest standard deviation. So we know it's going to be one of either C, D, or E. If the standard deviations are the same, which has the larger sample size? Well, as n goes up, the width goes down. Well, that means it's going to be this one because it has the smallest width. The first one will have the smallest width. So our answer to number 2 is C. Which of the following would result in the widest confidence interval? All right, widest confidence interval. As the confidence level goes up, the width goes up. So we probably want the one with the highest confidence, and 99 is the highest. So it's going to be either B or D. Well, then they said the widest, and remember, as sample size goes up, width goes down. And so we want the smallest sample size. So small sample size, largest confidence level will give me the widest. In a New York Times poll measuring a candidate's popularity, the newspaper claimed that 19 of 25 cases, so basically in repeated sampling, 19 of 20. Well, what is 19 of 20 if we did this in repeated sampling? 19 divided by 20 is 0.95. All right. And they're saying would be no more than 3 percentage points off. So they're telling me we have a margin of error equal to 0.03. What confidence level are the pollsters working with, and what size sample should they have obtained? Well, we're working with a 95% confidence level because they're saying in repeated sampling, they expect 19 out of 20 or 95%. So this tells me we're working with either D or E because it's a 95% confidence level. Well, they want the sample size. So I'm going to need to go back to my formula, which is P hat plus or minus Z star P hat Q hat over N. And what they told me here is that we are working with 0.03. So this equals 0.03. This part right here equals 0.03. And I'm going to need to look up my Z star. So second vars, inverse norm. So 95%. And I end up getting a Z star of 1.96. So I have 1.96. And I notice I don't have a P hat or Q hat. Well, if I don't have that, we always use the widest one, which is 0.5, or the worst case scenario, and that equals 0.03. I'm going to divide both sides by 1.96. This goes away. And we have, under the radical, we end up with, and I'm going to kind of run out of room here. We're going to have 0.25 over N equals 0.03 divided by 1.96 is 0.015. I'm going to square everything and divide. And once I'm finished with all my math work, once I'm finished with all of that, I end up getting, well, here, let's do this real quickly. So I need to square that. And this is now going to be 0.25 over N equals, I didn't square that, 0.00234, put that over 1, and 0.25 divided by that value, and I get up 1067.1, which rounds up to 1068. Remember, you always have to round up, even though that's a 0.1. Okay. Here's a sample of that work actually typed out because it was on the previous page. So there's the actual work typed out. Hopefully that will help you a little bit. Okay. Next question. A t-statistic was used to conduct a test for the null hypothesis against the alternative. The p-value is 0.056. A two-sided confidence interval for mu is constructed of the following, which is the largest level of confidence for the confidence will not contain 0. All right, so here's what we have. Now this was basically, they ran a two-tail hypothesis test, which means my p-value happens to be in both tails. And since my p-value was 0.056, I need to divide by 2, and I end up getting 0.028. So there's 0.028 in this tail, and there's 0.028 in this tail. Now, I don't know which side 0 is on. 0 could either be here or 0 could be there, but 0 is at one of the endpoints. I don't know which one, but it's at one of the endpoints. And if I get any wider, I'm going to contain 0. But right now, it's exactly at the endpoints. So what area do I have in between? Well, 1 minus 0.056 tells me I have 0.944. Well, if I go any wider, if I go from 94% to 95%, I'm going to contain 0. So I have to be less than 94.4 to not contain 0. Any wider will contain 0 because it's moving this direction. So I need a confidence interval 95, 98, 99 contain it. So the largest one that does not is 93. If 94 had been there, 94 would have worked. 94.4 would have been the absolute maximum. Okay. All right. So 0 is contained by anything greater than 94. All right. So this number 6, the school superintendent wants to know what percentage of property owners are willing to support an increase in school taxes. What sample size should be obtained to determine with 90% confidence to support within plus or minus 5%. So in this case, once again, P hat plus or minus Z star, P hat, Q hat over N. And they're telling us 90%. So I need a Z star. Second vars, inverse norm, parenthesis 1 minus 0.90, close parenthesis divided by 2. And we get 1.645. So 1.6445. Remember, this part's our margin of error. And they tell us they want it to be 0.05. We know we're looking for N. But what they did not give us in this case, once again, is they did not give us the P hat. So we always have to use the worst case, which is 0.5. And if I divide both sides by this, this goes away, and this becomes 0.25 over N equals 0.05 divided by 1.6445. I'm going to square everything. And that now gives me 0.25 over N equals 0.05 divided by this value. And then I'm going to square that. And I get a very, very small number, 0.000924. I'll put that over 1. I'll multiply the 2 on the diagonal and divide by the third number. So 0.25 divided by this is 270.55. If 270 been an answer, it's wrong. You always have to round up. So N is 271. That's our best estimate. And that's because I used all the decimal places. I let the calculator hold all the decimal places in. All right, number 7, 2 confidence intervals estimates from the sample are 72.2 and 77.8. This has a width of 5.6 and this has a width of 7.4. One estimate is at the 95% level and the other is at the 99, which is which? Well, if they're coming from the same place, the wider one will have the higher confidence level, because as the confidence level goes up, the width also goes up. So The 71.3 is at the 99% level, and the 72.2 is at the 95%. So this one right here is at the 95%. Let's check the rest of these. That's not right. Okay. So which is which? That's our answer choice. All right. I'll pause for just one moment here before I get a drink of water. Okay, continuing on with this particular problem. Let's look at everything that we know about confidence intervals. First off, we also know, and we're working with the mean this time, so x bar plus or minus t star s divided by the square root of n. Well, in this case, there's several things we don't know. We don't know the sample size, and the sample size can impact the width. Even though we took it from the same sample, we don't know the width. All right. So, because we don't know two confidence intervals from the same sample, we obviously do not know the sample size. So we don't know the sample size, so that's an issue. And we also don't know the standard deviation. And the standard deviation could also affect the width. So even though typically speaking, the confidence level increases as the width increases, and this would normally be the case in this particular instance, where things we don't know, so this question cannot be answered without knowing both the sample size and the standard deviation. You would have to know both, all right? Because you're taking a sample and samples vary, so you don't know if the change is due to the actual, you don't know if the change is due to the actual sample size, due to the confidence level, or due to the standard deviation. Because confidence level, standard deviation, and sample size all impact the width. So in this particular case, the answer is E, and that's a tricky question on that one. In a random survey of 450 adults, 28 said that they felt that their credit card debt is too high. With what degree of confidence can the pollster say that 28 plus or minus 4% of adults believe their credit card debt is too high? So what they're saying is we're going to need to take our confidence interval formula, p hat plus or minus z star, p hat, q hat over n. Well, we know p hat is 28%, and we know that this equals 4%, and we know we have a sample size 450. So we're going to have to work backwards on this. So we don't know z star. That's what we're looking for. So z star z star times p hat is 0.28. Q hat is just 1 minus that at 0.72 over 450. And that needs to equal 0.04. So let's do some work here with some math. So 0.28 times 0.72 divided by 450. I get that value, and I'm taking the square root of it. So I'm going to raise that to the half power. So z star times 0.02078 equals 0.04. So I'm going to take 0.04 and divide it by what I have, and I get 1.92. So z star equals 1.924. All right, so let's take a look at what this is. Remember, we're working with a confidence interval, and a confidence interval has two tails. We have a z star of 1.924, and then we also would have a negative 1.924, and I'm looking for this area right here. So I can go back And I go second vars, norm CDF, lower bound negative 1.924, upper bound positive 1.924. We're working with a Z, so the mean is 0, standard deviation of 1. And I get 0.9456, all right? So in this case, with what degree of confidence? Well, we're not all the way out to 95%, so we're gonna have to say we're at about 94.1%. That would be the closest to it. And I'm gonna pause this for a moment to check my math. Okay, so I went back and checked my math and everything is fine. I just carried it more decimal places this time. And because I carried it more decimal places, I ended up with a slightly higher answer. So once again, what I did here was I went second vars, norm CDF, and I put in 1.924, excuse me, the lower bound of negative 1.924, and the upper bound of positive 1.924. And I found that 94.5%. If 94.5% had been there, that would have been the answer. But it's not, so I have to go to the next one below it. So we can say it's 94%, but we're not a full 95%. Don't round up, okay? All right, number 9. A guidance counselor wishes to determine the mean number of changes in academic majors by college students with plus or minus 0.1 at 90%. What sample size should be chosen if it's known the standard deviation is 0.45? Well, that's interesting. This means we are working with the standard deviation of the population of 0.45, which means we're working with a different formula. We're actually working with X bar plus or minus Z star, standard deviation divided by the square root of n. Fortunately, we work the same way, but we're going to be working with a slightly different formula. All right, so we want a 90%. So second vars, inverse norm, parenthesis, 1 minus 0.90, close parenthesis divided by 2. We get 1.6445. So 1.6448 really equals or times our standard deviation happens to be 0.1, our standard deviation is 0.45 over square root of n equals, and please remember for this particular formula, this is my margin of error. My margin of error is 0.1. So in this case, I'm just going to take this and multiply by 0.45. And I get 0.7401. Over the square root of n equals 0.1. And by the way, when you're working with these small numbers, you are going to have differences in rounding. It's just going to happen. So I'm going to go ahead and put this over 1. Divide by the third number. And what that tells me is the square root of n equals 0.7402. All right, square root of n is 0.7402. If I square everything, I'm going to get my answer. And obviously I have a major problem here. So hold on for just a moment. I'm sorry about that. Sometimes it would help if I actually did what I said. So we're going to multiply the 2 on the diagonal and divide by the third number. So 0.7402 divided by 0.1 is 7.402. So the square root of n equals 0.7402, excuse me, 7.402. All right. And I'm going to square both sides and I get n equals 54.7. We always round up. So N equals 55. And this will be my answer to that problem, okay? And please be careful when you're working with the small numbers. Don't make careless mistakes. So 0.7402 times 1 whole divided by 0.1 gives me 7.402. And I squared that and got 54.8. All right, sorry about that. Number 10. A political action group wishes to learn the government approval rating on the environment. And we're going to use this ratio here. And you can always use this. This is the new sample size over the original sample size equals the change in width. So a political action group wishes to learn the government approval rating on the environment. From a past study, they knew that they will have to poll 270 people for their desired level of confidence. If they want to keep the same confidence interval and have a margin of error 1/3 of the size, how many people will they have to poll? Well, we have our formula 1 over the square root of, we're looking for this new, over the original was 270 equals in this 1/3. All right, so we got a little bit of math to do here. So I'm going to say let's square both sides. Okay, so when I square both sides, I end up with 1 over the square root, 1 over n divided by 270 equals 1 over 9. Now I can make this side look a little bit bigger, better. This would probably been better shown if I'd put a double line here, because then that rewrites as basically 270 over n equals 1 over 9, because all I have to do is take the reciprocal of that and multiply. So 270 times, 270 times 9. And I end up getting 2430. So in this case, n equals 2,430. All right. And once again, the trick to that is write the formula, plug in, square everything. So this 1/3, everything got squared. So this 1/3 became 1/9. 1 squared is 1, and the radical was removed. So there was no funny business here. And then we're going to flip this. So this will go in the numerator and the n will be in the denominator. That would be the reciprocal for some quick math. And we have 270 times 9. So in general, how does doubling the sample size change the confidence level? So I'm going to go back to, we started off with this formula that we tried out today. 1 over new over original. And let's just say that originally we had a sample of size 200. And now we doubled it, so we have a sample size 400. Well, 400 divided by 200 is 2. So we end up with 1 over the square root of 2, which is 1 divided by, and the square root of 2 is 2 raised to the 0.5, 1.414. So we're basically dividing it by 1.414. So we're taking the original and divide it by 1.414. The next one, a 90% confidence interval is to be created to estimate the proportion of television viewers in a certain area who favor moving the broadcast to the late weekend news to an hour. Initially, the confidence interval will be created using a sample of 9,000. Assuming that the sample proportion does not change, what would be the relationship between the width of the original that is based on a sample of 1,000? So we're going to go back to using this formula. All right, we're going to use this formula. And so we have 1 over the square root of the new over the original. Well, the original in this case was, our original was 9,000. And our new is 1,000. So this is 1 over, this reduces down to the square root of 1 over 9. Well, that becomes 1 over the square root of 1 over the square root of 9, which is 1 over, please don't forget the double lines, 1 over the square root of 9 is 3. So 1 divided by 1/3, and basically that's taking a reciprocal or the flip. So that is 3, and if you don't believe me, 1 divided by parentheses 1 divided by 3 is 3. So it would be 3 times the width. All right, the second confidence interval would be 3 times the width. Now let's think about this. If we decrease the sample size, as n goes up, width goes down. As n goes down, width goes up. So we know, just looking at it, we're going to have to be wider. All right. So the question is, how much wider? So we're not going to be 1/3 or 1/9, and we're not going to be equal. So it has to be one of these two. And it's always a relationship of the square root, because n is in the, because part of the formula is either p hat plus or minus z star p hat q hat over n, where n is under the square root, or we're working with x bar plus or minus z star, standard deviation divided by the square root of n. And once again, it's under the radical. So whatever that ratio is, so it's the square root of the ratio. So basically the ratio was 9 over 1, square root of that is 3, and we knew we had to be wider. Okay. All right, I hope that helps. I'm sorry this one was a little bit choppy and I had a couple of errors that I had to fix on it, but I appreciate your time, appreciate your watching, and look forward to seeing you on the next one. Thank you.